Hello everybody, welcome to another stream. How are we doing? So last stream we continued on trying to get this shader together. This will construct leaf spheres for the cluster tree. We kind of got it mostly there, the initial sketch out for it. But we're just finishing the end of it off. And we should move on to another shader after that. Hey there, Seg4. How's it going? Thank you so much for the subscription there. Appreciate it, sir. How you been? Ooh. So, we kind of got a little bit stuck on. Well, I got a little bit confused last stream. How atomic compare and exchange on GPU is not like the CPU one, where it doesn't return a boolean. It returns the original value, so it cannot be used to build a sort of like a way to take away from an integer. Basically do like an atomic sub, but only one thread does it at a time. So you can make sure you don't underflow a value or something like this. So this is probably more complicated than it needs to be. Yeah, we'll fix this and make it dead simple, and then we need to just allocate a child node here, and then we should be able to move on to another shader after this one. But yeah, when I had some time off, been working on my side project renderer. Awesome. What is this something you've just started, or have you been working on it over the past year or something like this? Okay, so basically each thread in this shader gets a sphere, and it traverses down a tree of clusters. Clusters are 2 by 2 by 2s, and every sphere can have a child node as well, which takes you down to a higher level of detail, which is another cluster which represents that child sphere. So the basic idea is when we reach here, if we're the thread in the cluster. Oh my days, I just realized I've just found a problem with the shader. We do an early return, don't we? Wait, this might be fine because they all will go in that cluster. Yes, it's fine. Should be fine. Yes, this code here is literally just saying, oh, wrong one. This code is literally just saying if I'm the first thread within the cluster which has 8 spheres in it, do some work which is should only be single threaded, right? Yeah, and we have spheres in our cluster. And let's just get the next free index. So what I want to do is, so we're just trying to allocate a group of eight spheres basically. So the problem is this is a persistent piece of memory. It's a persistent memory allocator. So you basically need essentially like a free list of 8 spheres. So I was trying to get around by maybe having a free list, and then maybe if the free list is empty, just bump allocate. But that's just going to create more complicated code, and it might just be better just to like as the game runs, you'll just be doing this free list indices anyway. So I think we'll just pre-populate that array at the beginning of the game or something like that, and just use that from then on out. But this doesn't solve the problem of having to take away one and underflowing. Well, what we'll probably do is just do a atomic sub U32, and then we'll probably on this variable here, and get our free index this way. Oh, wait a minute. You'll get the old value. It should never underflow. Like the whole point is like maybe we should ensure that it will never underflow. Something like this. We should be able to delete all of that. Oh wait. So fish had the free index. Oh, the index of where the group of 8 spheres are, and then we can essentially. Good, that's not a thing anymore. Then inside our cluster, we can basically just store that in there. Then we've just got to copy the spheres into that new array, basically. So it's got to perform the copy now from LDS into that new allocation. About 8 months has probably been the 10th attempt to make it one since I learned Vulkan. Find out something useful now. Awesome, that's good to see. Yeah, it is a lot of work to learn Vulkan. It's a very complicated API, but after you've learned it, it's one of those things where it's like, yeah, it's quite easy to kind of understand, but then actually like putting the work into to get a renderer off the ground and working it is still a lot of work. But yeah, just one of those at the moment. Things you have to do, unfortunately. But that's good to see you get something going. Are you doing like a 2D or a 3D renderer? Two seconds. I just have to check on something. I'll be right back. I'll be right back. Right, welcome back, everybody. Yeah, so you're doing a 3D renderer trying to replicate rendered scenes from Blender Transformer Renderings. Awesome. Nice. Very cool. Awesome. Have you got like a little custom plugin in Blender to sort of like export the mesh data into a little custom format, or are you using like a standard format for that? Hey Nico, how you been? Merry Christmas. Or yeah, happy holidays. So just got a copy of the spheres now from LDS memory. So it's in this like we got this LDS memory which is basically shared between this group of 4x4x2, which means you fit 4 clusters. 4 clusters of 2x2x2 in here. So you got an array of 4 of LDS memory for this 4x4x2, and that if statement where we allocate an array of 8 spheres is for a cluster, and it's got a spheres count in there followed by 8 actual spheres. So we just got to copy those guys into there. But theoretically we should have all 8 threads. So we should just be able to get each thread to do the copy. So this is saying, like, so what we should do is something like this, right? So we'll be like, hey, if there's any spheres, let's let the first thread in that cluster allocate ourselves a slot, right? So we say first thread in the cluster of 2x2x2 will allocate us 8 spheres, contiguous. Right? So it allocates those boys, and then each thread just basically sets it. So you just need to literally just do something. Okay, so you got a bit of a... Oh yeah, you have to just read it from here. So you have to read it from there. We could do read lane. We just have to know the lane though, unfortunately. Yeah, I don't know how easy that's going to be. You could use a read lane instruction and everything just reads from lane, whatever. So you have this sort of as a scalar vector, sorry, a scalar SGPR, right? And no, sorry, it's a VGPR. And then only actually no, it's probably not a good idea to do it this way. Yeah, so I was thinking maybe we could like have, so it'd be like probably about, yeah, there's 4 clusters, so 4 threads will have like a different start index, and the rest of the threads will find their sort of main thread that allocate those spheres and sort of read from that lane and get the VGPR into the rest of the threads basically. But probably not a good idea because it'll be a calculated index, and I don't think that's supported on all hardware. So we'll just read it from where it's set it. It won't be as good, but it's cached, so it should be fine. So yeah, we just want to like basically read that out like that. You know, and maybe if it's, I don't know if the compiler will be smart enough to optimize that, to be fair. But anyway, It's only done once at the end of a shader, so it should be fine. So now we literally just get the spheres and copy them in there. So I think it's just... oh, let's find it. Volume spheres. Right, there's our boy. So... do you use any other editor for debugging? What's your toolchain in C? Right, I just use GF when I do debugging on the CPU. GPU, I just use print. I just print from a shader because I've got my own like shader compiler, so I've got basically printing in it. But I use GF, and GF is like this. It's a GDB front end. So it's just a UI to GDB basically. I can't really show much about it, but there is a GitHub for it. But yeah, debugging could be a much better experience, but you know, this is sort of the best sort of stuff we got, unfortunately. That's what I use. You got custom GLTF importer. Only remapping y/z coordinates to make it easy to use with Vulkan. Oh, okay. Gotcha. Yeah, it makes sense. Because then you can like bring in meshes from any tool, right? If you support that. That's standard, right? Which is great. Oh, M2 is it? Fair play. I'm trying to embrace LLDB directly. It's been hesitant before because used to crash on simplest of things, right? Yeah, no, I honestly, it was very confusing when I booted up the first time, LLDB, and I never bothered to try and learn it. You know, it's one of the things with CLI-based applications. But yeah, the user experience is not usually the best. You have to try and find some places to read up about it, right? But yeah, I wonder how it compares to GDB. If the user experience is any better, like does it, you know, because doing like a watch point on a memory location in GDB is faff. You have to print out the address and then copy the address, cast it into the thing you want, dereference it, say watch this dereferenced casted thing, memory address. It's complete crazy. And I don't know. Yeah. Okay. All right, I'm gonna take a look into it. You know, 'cause it's always good to learn a CLI tool because then you look like an absolute wizard, you know, an absolute boss. CLI is good editor. I have a student license. Awesome. Yeah, when I first looked into CLI, I was quite impressed considering it was written in Java. But yeah, I prefer things a little bit more lightweight though. Oh, is it really much better than GDB's? Fair play. I'll take a look into that. Volume spheres. So you just literally get so you've got to get your sphere start index, and you add whatever your cluster sphere index is, and then it's just as simple as this. Equals, where's that? Oh yeah. So then we just copy it from LDS out into main memory. Each thread does that, and kabam. So that's how we'll end up copying the spheres out and allocating it for a specific node. Yeah. Now this is a bit of this is a. We're basically going down the tree of these clusters, and we're trying to build the tree one level at a time. So we start on level 0, do all of the spheres for that level. It's better off if I get my previous drawing out for this. Ah, here it is. This lovely guy. So start off on level 0. It's only got one node, and we'll go over all the edits for this. Then, when we've gone over all the edits for this and worked out any of the edits that should target this guy, we get to the end of the shader and we go, oh, was there any edits that went past this level? And if there were, we're going to allocate a child node for each of the spheres that have edits that are higher level of detail than this one. So then we do another dispatch over level 1 and go over all of those nodes by traversing down the tree from the top until we get to our desired node and our desired sphere that we're targeting for each thread, right? So this is a cluster, and each thread targets a sphere in that cluster. And we repeat the same thing, right? We check to see if the edits go over these spheres, and if they end up going over them in a higher level of detail, then we'll end up making a new node and all that, right? So this is all we've got to try and do here. Now, I've got to refactor some stuff because I was doing some thinking today of how I was going to deal with the allocations for this stuff. And wait, let me see if I can quickly sort this bugger out. Where's the globals? Here we go. Stack count, capacity. Gotcha. Okay. So, right. Okay, let's get back to where we actually were. So, yeah, I've been thinking off stream how we're actually going to do the shaders after this one. And basically, we need to know the leaf nodes. And I've been trying to think how I want to solve this problem. Because when you make this tree, this guy could be a leaf node, but these ones could end up creating more nodes and all this stuff, right? With more clusters and you know, and basically, we need to know the leaf nodes so we can start our threads on the spheres of the. Is it no? Yes. Start our threads maybe on the spheres of that node or the node itself. But anyway, so something like this. I need to keep a list of these guys. But the problem is when we do the initial build, we're not really going to have the final set of leaf nodes. We're going to have an intermediate set of leaf nodes. So we could just pump out an array of indices. Right, that's one way of doing it. But then you need to worry about some other memory allocation, right? So I was thinking, why don't we keep all the leaf nodes in a contiguous block of memory, right? And then you just basically go, oh, I've got 7 leaf nodes. So you just dispatch 7 threads, and we don't do 7 threads, that's too small. But you do, as an example, that's a very small model there. And then we can just basically know based on how many leaf nodes that we have, we can just simply find those nodes in a contiguous block of memory, and then traverse up the tree and do all the LOD selection or LOD calculation work that we're going to be doing next, because the next stage is we're going to essentially do something like this, right? If so this is a cluster, right? But it's not a leaf cluster because it's got children. But if the children are all leaves and they've got a full set of spheres, we can then get rid of all of these guys and then just replace it with that, right? It's basically simplifying the tree, because this will essentially be like a block of 4x4x4, which has a 2x2x2 of 2x2x2s, right? And we only want to do this actually, there's another condition, is if they are completely surrounded by a layer of clusters from all sides. And if that is true, this is basically like too much detail than we actually need because it's not surface, right? We only need the detail on the surface. So we'll basically just reduce this to maybe, hopefully, a single sphere, but probably a larger set of spheres than what they were. So we need to then get rid of these leaf nodes. And then because you're getting rid of leaf nodes from an array of leaf node indices, you basically have to like repopulate another array or something like this. So the way we're going to solve the problem is this be contiguous in memory. So we just got to convert to this new mindset. Thank you, Fit Writer. Appreciate the compliment. Probably shave off around Christmas time though, to be fair. We'll see how it goes. Volume. So go to the volume. So basically, I've got the cluster node. The cluster node has a start index, and then all of its children nodes are contiguous. I did this to save memory on the cluster node because we're going to be having a lot of these guys. But yeah, I might have not saved memory to be honest, because you would create excess nodes. But yeah, it's not a good idea. So I think what we might do is just have the children node indices. I always have 8 of those boys there, you see. I don't know. Okay. We can definitely optimize this later to bring it down to less memory. I'm sure we can work that one out. So the way we're going to do this, so it's like how can you make the leaf nodes contiguous? What's the strategy behind that? How are you going to manage that? So there's 2 different ways you can achieve this. You can basically can figure out like, oh, I need exactly this many nodes. And you allocate all your non-leaf nodes from the left, and you allocate all your leaf nodes from the right. But we don't have this, unfortunately. So what's the next best way you can do it? The next best way is... Wait a minute. Yeah. So yeah, if you know exact, it's amazing because then you won't get a hole in the middle, right? If you get a hole in the middle, where there's a big gap in the middle where you've underestimated, that's not good. So how do you get around that problem? You just got to rethink about it. Think about it different ways. So the other way you think about it is you have a worst case of what it's going to be, and then you basically have a midpoint. Now the beauty of this is, or is it the beauty of it? Wait, that's a binary tree. Anyway, there's a certain... Yeah, so for a binary tree, it would be in the middle. You can use the number of leaf nodes to work out the number of... but this is an octree. So of an octree, it's probably a little bit different. But the basic idea is this. You basically have a cursor, and then on the right hand side of the cursor is where the non-leaf nodes go, and then on the left hand side is where the leaf nodes go. And whenever something becomes not a leaf node anymore, you can just basically take it out and bring in one of the nodes from the end of the array to replace it. And you can patch up the references for it because it's not hard. And then it means if we don't fully utilize the memory, we've got two options. We can either copy this out into a different place, or we could just be like, well, we've got 2 blocks of memory which are not utilized yet, or something like this. I think we're going to need a defragment process, because we're dealing with like persistent kind of heap allocate things, you see. So we're going to probably need a defrag process that will basically just copy a block of nodes around. And luckily, all of these nodes reference each other via relative indices from this center cursor point. So copying it should just be pretty easy. We don't have to fix up any references anywhere. So it should be quite ideal. So yeah, let's get going on that one then. Just got to change that. So we'll still have a root node index. For main rendering, not used when constructing the tree. I don't know, these things are old comments, let's get rid of them. So I want to say, let's just get rid of this crap. So I want to basically say, you know, leaf nodes come before, and non-leaf nodes come after. Now the question would be, what happens if you only have an LOD1, right? So an LOD0, and there's no more levels of detail past 0. Doesn't that make the root node a leaf node? And the answer is yes. So I guess the way we solve that problem is we can basically say, like, that's a very small model with just one cluster, which could actually happen. Yeah, but so in this case, it's not the root node index, so we should really call it something else. We should probably give it the name of we should probably give it the name tree midpoint cursor. Let's call it a midpoint cursor. Ought to be good enough. So right, so when it comes to so I think we made the necessary changes now. Now I'm just gonna go through the shader that we've been working on the past few streams, and we're just gonna patch those lovely things. So children node start index, this boy. Children node start index, this one now becomes children node indices. This saying it doesn't have any children, so you got the children bit set for that. don't know if that's true. I'll double check that. What is this? Oh, this is in some code we should have probably deleted by now. Right, let's get rid of that. Right, some old code. I'm just keeping around just in case I want any of it. Right, so that was that reference there. Now we just got to change this. There was a root. Let's go. So how do we know where the root index is now, you know? That's one thing that we've... The most likely it's going to be 1, but it could be -1. So realistically, we need a couple of bits for that. Oh no, we need is 1 bit for that realistically, right? All you need to know is if you need to go before it or after it, basically. Oh, Benny Montana, how's it going? 25-month streak, look at that. It's over 2 years. Amazing, thank you. Appreciate the support. How you been? Yeah, things are going good. Just been chilling, been off work, so it's been mostly relaxing, exercising, just Christmas shopping. You know, doing life stuff, looking after the baby. But yeah, things are going good. But yeah, we're currently in the middle of some like big old, like, right, we know what we want. Let's design this big old mega plan. We designed it, and now we're just like executing mega plan of achieving LOD and clusters and trying to render tons of spheres. So it's been yeah. So we're currently just trying to get something minimal working out of this big mega plan, you know. Been busy end of years, sprints at work. Oh, okay. That's gotta get those. Yeah. Yeah, gotcha. Yeah, do people at work not take like a bunch of holiday though? At the yeah, I don't know. Well, it depends where you live, isn't it? Some people don't take holiday around Christmas, so at different times. How's the baby? Yeah, baby's good. We're currently trying to get him to sleep by himself, so he's in sleep training. Um, he's a he's doing well at it sometimes, but he's not learning from it during the day. So do it at night. But he's not good at falling asleep by himself at the moment. How's the baby? Oh, baby is 4.5 months. So very new. But yeah, it's a lot of fun and work. Yeah, little boy. Like he's just started to sort of roll a bit now, and we had him in the cot, and he had these little elephants up, dangling in his little rocking chair rather. And he just sort of like right, what happened there? Okay, it's just the music going. So and he just sort of was looking at us and giggled, and then just like swung and punched the elephant and tried to roll off. So they do the most silly things sometimes. And he did it again as well. I did the action of like, oh, you know, punch the elephant, and then he was just like, and he just went. It took him about 10 seconds or so, but then he did it again, and it's just so cute. Stuff needs to get delivered by end of year, so yeah. Best just babies sleep when they sleep. Yeah, that is true. That's good. Good. Yeah, I was gonna stay up late last night. We ended up not doing that because of that logic. Definitely a good idea. You're very cute in the early months. Mine's 6+ now. Miss those days. Yeah, yeah. There's just so many aspects of them which is just like, like when they're not crying and screaming, there's so many aspects of it which is just, just puts a smile on your face, Um yeah, and then they scream and cry and you're like, ugh. Yeah. Our 20 to 10 now. Things move so fast. Yes. Yeah. Kind of. Yeah, for me, it's only been 4.5 months, and that has been fast. I can't imagine a time before that also. Yeah, weird. Very weird. But it's not quite 10 years yet, but it will happen like that. Yeah, 2 seconds. I'm just gonna. My wife's just come home. I'm just gonna give her the baby monitor, and I'll be right back. Just give an update on how it has been. Right, BRB. Right, I thought I heard her come in. She didn't. Okay, so maybe not. Anywho, so where were we at? So that root, whatever. So we need to find the root node somehow, and it could technically be off the midpoint cursor on left or right. So we could call it like root node. Yeah, I don't know what I want to call it. Root node is after, right? It's a little boolean. Yeah. Because it's going to be the first thing allocated. And oh, I don't know, but it works differently to every other node. It's really annoying. Oh, you will know. You will know. If your nodes count is 1, then it's before. If it's got a leaf node, it's 1 after. Right, okay. So where's the root node? Okay, so we need to just... So when we reset a cluster... So there's now start nodes... You can work out the start index by doing midpoint cursor take leaf nodes count. Right. Okay. So your root. So when you initially start this thing off, it's going to be So when you reset a volume, and then it needs to go and run through the process of being constructed from those list of edit operations. Where's the root node going to lie now? Well, we could just always put it... Actually, yeah, I think we'll just stick it. It's got a volume cluster in it. Alright, I have an idea. Yeah, so right now, if we just stick it on index 0, so it's going to come after it. But okay. Number of leaf nodes we do not know yet. Number of actual nodes, we kind of do not know that yet either. But we had a count come in. So it was a way of saying the capacity so we can bump allocate it, but it's not a good idea anymore. Yeah, we'll just ensure that we have enough. Okay, so where's that root node? Right, there's only one, basically one of those guys. So from the midpoint, then we add this sort of cluster node index. Now these cluster node indices, they've got to be signed now, right? Because we can have negative ones now. So it does use up an extra bit for a signed bit, but should be fine. You know, I don't know if we're going to want to squish these down to a 16 bit, so it should probably be alright. Oh, it will be alright. That's what I mean. Right, that's the dead code. Okay, so all these node indices, S32s. Did I just say children's? Can't believe I wrote children's. People's. Okay. Right, I think we're basically there now. So there's the changes we need to make to the structure. Now we can do the allocations. So as I was saying with a shader, we're simply trying to construct the leaf node, construct the whole tree and find the leaf nodes and leaf spheres. So at the end, we'll know whether we need to actually allocate a child node for this sphere, because there's been some higher level of detail edits, so we might need to go off and construct ourselves another cluster. So we can, in a future dispatch, after this one finishes, it will then construct the spheres in here that are needed. So what we're going to do is so this is now nowadays. So we're going to assume that this is not a leaf node that we're making, but then we can know if the current one that we've finished on is a leaf cluster, and then we can move it into the right place, something like this. I think that's right. So right now we'll just assume that it is a so it's sort of midpoint cursor, and let's go and find our volume. Excuse me. So we basically want to get the number of nodes, up that by 1. Oh, this is where it gets a bit difficult, isn't it? We kind of need a leaf nodes and maybe like a non-leaf nodes count. That's probably the way we're going to roll. Okay, so it's the bottom again. So this way we can just atomically increment these guys and allocate ourselves a node from that basically. So we can just do a lovely free index equals atomic add e32 address of volumes. Ooh. Volume index dot this guy by 1. Then we've got ourselves our index now. We're just to make it a non-leaf node. So after you've allocated it, what do you need to do? Good point. So let's look at the cluster node. So you've definitely got to assign it these sort of like positions, like a position. So let's go ahead and actually get this. Get it all set up. So to get the absolute index, what we need. Ooh. I need that. Yes. So that one needs to go there. This one will need an absolute node index. So again, our node indices are relative from the midpoint cursor. So yeah, that's all we're doing. So we're just going to make one of those boys, basically. Now, so let's get all of the fields in and see how they need to be initialized. So we need a left. How are we going to make a left? So based on our current node, that would be this one's left. Okay, good. So the root node did get set up right. So this is going to be like a times by. Okay, so it's 2 by 2 by 2. So I think is it just times by 2 then plus. Oh, there's a certain offset in the. There's a mod. Yeah, this is it. I think that's right. So so level 0 is not a good example because the position of it at the level of detail is always going to be 0. There's only one cluster. The next level of detail is 2 by 2 by 2. So if you're at 1x, 0y, 0z or whatever, for this guy, imagine. when you want to refer to the child of this one, that is going to be how are you going to define the offset for this guy in a grid, right? So this one will be 1 by 1 by 1. This one will be 8 by 8. Sorry. It'll be 2 by 2 by 2. The next one will be probably 4 by 4 by 4. Of clusters, right? No. Yeah, because that's it's just 8. Yeah, 8 then 64. So 64 is 4 by 4 by 4. So this would then mean that you've got, so if you have your offset, which is like 1 times by 2 will get me 3. So I'll start on 3, that makes sense. And then plus whatever the sphere is in here. Yeah. That's right. That makes sense. Yeah, so this would say plus whatever the sphere index was within inside that cluster. So since it's 2 by 2 by 2, just mod 2, and that'll get us to 0, 1. Wunderbar. Exactly, wunderbar. Hey Tech, how's it going? Welcome. Left, bottom, near. So Y, Z, Bob's your uncle. So parent node index. So remember, that's not the absolute one. So the parent is just cluster node index. Oh yeah. Then this sphere's start index, E32 max. Cluster node indices. Now these guys, I really don't like the fact that, yeah, first of all, they're S32s now, but we've got like 8 of them. So 1, that's like 32 bytes of memory. 2, I have to initialize all of those 1 by 1, right, in shader code, which I prefer not to. But I think it's the only option, it's the best option we've got, really. It's the best option we've got. So do a lovely for loop. Oh yeah. And then we initialize the bit set. I'm not sure if we need the bit set. Hopefully we don't. So it's one less 32-bit integer. But anyway, so it's kind of cool. It's got to find the reset. But we initialize these boys. Here we go. I missed those there. Right. So, are we done with allocating a node? So we've got to solve the problem for those leaf nodes now. Like when we construct it, when we finish a shader, we need to make sure we have a contiguous array of leaf nodes. And we haven't solved that problem yet. Going alright, hope you're doing well. Got a dash. Happy holidays. Happy holidays, you too. Thank you for the oh, Amadeus, thank you so much for the donation, whoever that was. Appreciate it. And happy holidays to you. Um, cheers. So righty-o. Leaf nodes have to be contiguous and they go negative to on the negative side of midpoint cursor. So how are we going to do that? How do we... So we know when a node is a leaf node because you're processing a 2 by 2 by 2, right, of spheres in the same wave, right? The same lockstep executed compute unit thingy, right? Furthermore, there's actually like 4 clusters, right, which is a 2 by 2 by 2. There's 4 of those guys in the same wave, but that doesn't matter. All we need for this problem is the fact that they're all in the same, executed in the same wave. And so this point here, basically we want to know for our cluster, like we've got a spheres count, right? It's right here, spheres count. So if that's something, wait, no, that's not right. Excuse me, it's not right. We might, okay, so in this LDS memory, they're shared between all the threads. We might need another, let's make it 10 integers. I'll be wrong. Well, we haven't used the children bit set, actually, thinking about it. Think about it. Oh, we have to set up that children bit set. Right, so here okay, we didn't set up, okay, there's a few things that we missed from this. For the parent, we have to adjust a few things. The first thing is we have to set this children node indices. What is our child index? How are we going to know that? Oh, yeah, I know. So we flatten that coord in and do this. Coord at constructor LOD, that's all we want. So we basically just flatten out like what sphere. Oh no, is it called a sphere index? That's it. Plus the sphere index, perfect. Plus the sphere index. Yeah, then we set that to whatever node index is. Bear in mind, these have to be S32s. Okay. Then we have to assign children bit set. Now, the things about children bit set is the following. Like this one is thread safe, right? Thread safe as we own this as sort of a single thread writes to the writes to this location, whereas the bit set 8 threads are gonna do it all in one go. Now they're all gonna be in the same wave, so They are doing it in lockstep, so technically you could probably use a wave intrinsic, but it gets complicated because you've got multiple clusters in the same wave. So we're probably better off just using an atomic, and it's only done once anyway. So I need to bust out the old HCC atomic intrinsics. I think we have a bit. We have bit ones, right? Bit or. Right, and it returns you the old value. So it's a bit or U32. And then away we go. So address of this one, and we just want to shift in there. One shift left that, yeah? And that'll be your bit for the child. Let's double check that quick. Jobs are good. Right, so that's not thread safe, so that's just not right. Okay. Very good. Very good. So now the next thing we need to do is sort out the right, what's the next thing we need to sort out? Yeah, how do we know which one is a leaf node and put it in that contiguous block of memory which comes before the midpoint cursor, rather than just keep putting them in after that, right? So when none of your spheres have an alloc child node, none of them do this, then this means that this current node that you're processing is a leaf node, so it needs to be moved. And the beauty is no other thread will be touching it anymore, except for you. So you're free to move it around, basically. But the tricky point is we have to somehow move it while things are doing this at the same time. While they're adding non-leaf nodes. We have to move it from the non-leaf node array into the leaf node array. So that might be tricky. Yeah, it actually might not be possible to do it. So we could handle it in post somehow in a second pass, as long as we know that we can still put it in the contiguous array. Yeah, so you don't know until you've processed all the edits for that node. No, you might be able to tell. You might be able to tell. When you go over all these edit things, right? And what you're doing is you're keeping track. Like, basically, we're trying to construct a cluster tree. A tree of clusters of 2 by 2 by 2 spheres. And we're doing this from a bunch of simple edit operations, like basically painting a sphere down or a box. And just seeing if it... And we're doing it in some cluster tree. So we can basically save space where there's not any data, basically. So we'll go over all of the edits for this node and just see if they color in any of the spheres in there. So so when you do your edit operation, there's a target LOD. So the cool thing about this is you can say, hey, I want to make a very big sphere. Yes, it basically determines the sphere size, right? You've got the LOD 0, which is the lowest level of detail, and that's the biggest sphere you'll get. But you can only paint in a 2x2 of those within the volume. And then as you make the LOD higher, you can paint more spheres within the volume, and they'll overwrite the lower level of details and all that stuff, right? Now, the thing I'm thinking about is you can kind of know if the next set of children from you, can you? Our leaf nodes, maybe. Because you basically just look at the edit and you go, is the target LOD? If it never goes more than 1 plus my current level of detail, then that means the children of mine are not going to have children, right? So those will be leaf nodes. Basically, and we know it hit this parent node, which means it's definitely, we know it colored in one of the spheres here, which means it definitely will color in one of these guys, maybe. I don't know, I think that's a bit because yeah. We know it colors in a sphere, so it definitely colors in one of. We know it would have colored in one of the spheres there, so it's definitely going to color in a sphere in the next LOD, making it a leaf. So we just got to see if there's any problems with that idea, basically. So if you can predict that, then it means that you can simply predict whether or not when you construct the child itself, whether it is a leaf node or not a leaf node. And it's that simple as that. And then that would make it far better to work with, I think. So given when the target LOD that we're painting down, if that is bigger than the current one that we're constructing, because we do one level at a time, and put synchronization points between those. So this one's saying we're removing a higher level of detail. Wait. Yeah, this removes our sphere. And it says allocate a child. Perfect. Now what we want to say is alloc child node is leaf. Right. Now the beauty is you only need it when it gets set to true, and you just go, okay, is edit you wait a minute, maybe you, because you might do it multiple times. So you or equal, so I have to make it false at some point. So we or equal on it. Edit target LOD is greater than, or plus, no. Is equal to BC construct LOD plus 1. Right, so if that happens all the time for every edit within that LOD, sorry, within that node, if that wait a minute, I just got to double check that. So let's set it to false there. Let's get it all set up and we'll double check it. When you remove, what do you do when you remove? You're removing the current level of detail. So high or low when it's equal to the construct and you're removing. You haven't put anything down yet, but you should probably get rid of the children. No, you're removing the current level of detail. Yeah, that's fine. That's fine. That's fine. That's fine. Right. So each node like sphere has its own, possibly has its own node it will make, right? Child node it will make. So there's one of these booleans for each of those spheres. So if the level of detail is less than, we don't need a child node, so we just reset that. If it's greater than the target, if the thing that painted down is greater than the current one we're constructing, yeah, if it went over this sphere and the target that we're painting down, if that goes any higher, I know I should probably make it and equal, isn't it? Right. So if we make it and equal that, so we go, okay, if it's if the level of detail is more than target LOD that we're painting down is more than 1. Yeah, if it's if it's 2 or more LODs ahead, then it means this child must not be a leaf because the children of this node will have children of their own. Okay, that's good. So then that means when we do this thing down here, it should be very simple. We just literally say, just do this, right? If that, then we just do the atomic a bit differently. The compiler will optimize this to make it better. I'm not fussed about making it. We could technically, I think my compiler will have a bit of a weird time doing this right. So we can't store pointers in local variables because pointers are a bit of a hack, really. So if it is a leaf, we use the leaf nodes count. If it's a non-leaf, we use that. Now, if that is the case, it's a negative index, right? So it'll be 1 take this, yeah. Jobs are good. So that's how we deal with the leaf nodes. That's pretty sweet. I like that a lot. So now the question is, what is left to do? I think we want to now make the next shader. And I think it will be the last shader that we need to make until we can start. Well, no. It's the last shader which involves constructing this cluster tree until we can actually test out some base version. We still need to adjust the binning shader that we've already written out to use this new volume data structure. Yeah, still doesn't work to do, but at least we can probably start firing this thing off soon, or just gonna compiling. I got a whole bunch of comments in here which are just so wrong, but it's been helping me sort of try and understand this problem. But essentially we want to make something yeah, I need to go over all this code that we just made and clean it up, put it in the right place, and sort out these docs. So essentially we're going to make something like this. So we're going to go over all of the leaf nodes. So refine LOD. So what's the plan? So we've constructed some portion of the massive, potentially massive 1024 cubed volume of spheres. And the reason why we've done some particular subsection of it is because just doing 1024 by 1024 by 1024 is one, it's a whole load of spheres. And unfortunately, the way I've had to end up designing the algorithm is we need to allocate for the worst case, which is basically 1 billion spheres. So we're better off breaking it down into some subsections if the volume is to go greater than maybe 256 or 512 cubed, right? I'm not quite sure on the number yet, but that's the direction we're going, and it's not that bad. So what refine LOD is going to do is it's going to go over all the leaf spheres. So after we've constructed one subsection of it, we'll go over all the leaf nodes and we'll just refine the level of details. We will just have the leaf spheres in there. So we'll just have the leaf nodes and leaf spheres. And we need to find a way of basically saying, hey, we can get rid of a 2x2x2 of clusters and turn it into a single cluster of 2x2x2 spheres. Because basically it's surrounded by a bunch of clusters. So we can instead of making it tons of smaller spheres, we can make it one big sphere. And we can save on a whole bunch of space and memory and free up a whole bunch of clusters back into memory. Right, because it's completely surrounded by spheres. And we will not see it. And if we do see it, it's because it's kind of animated a bit, and that's fine. That's fine. It's part of the style. So there's refining, there's simplification, but there's also refining LODs, meaning if a child node, say if a sphere has not been placed here, but it has a child node, and that child node has a full volume of spheres, well, we need something that's lower level of detail. So when we zoom the camera out, we're not rendering these things which are sub-pixel. We render the largest sphere, which represents those cluster of spheres. So that's the other job this thing is going to do. And it's going to retain the list of leaf spheres. What is your opinion on Rust for personal projects? Why should I use it over C? I don't know. Like, in my opinion, Rust is a great language to, when you're coming down from high-level languages like JavaScript or Python, to sort of get to grips with the more lower-level side of things. You kind of get similar kind of tooling with like a package manager and all that stuff, right? But you can start peeling back the curtain and start understanding system stuff. But given probably default human, the default way humans typically work is they won't really peel back the curtain and and some people are probably better off being chucked in the deep end if they really want to learn the low level stuff. But yeah, long term, I don't think Rust is a good idea. It's just not like, it's very complicated and it enforces you to, like, it's a complicated language now, and it just forces you to design your code and data structures in a certain way. You'll be typing out some code and you'll be like, oh boy, I can get this thing compiling. Borrow checker says no. You have to refactor your code because double mutable references, and yeah. And then using unsafe Rust is just too much typing, right? Yeah, C compiler goes brewer. That's another point. There could be something better than C. Just saying, but there's kind of kind of not anything that's fully worth switching off it. At my point. Um, yeah, but the beauty of it, SPIL, is like you can look into the source code of Rust and start understanding how the low level stuff works and sort of learn. Because to be honest, it's a modern sort of, it's a fresh look at it's just got some good modern takes on sort of abstracting stuff. Like some stuff in the standard library isn't that bad. It's quite good actually, but they definitely did standardize too early. And there's a few things where it's like, why didn't you finish that before stabilizing on 1.0 and basically not being able to break this in the future? Yeah. Do you have any advice regarding generating crash dumps? Oh yeah, K-Monk, I got you back, my friend. Literally the first episode of this stream, of this series on the VOD channel, we did that right away. Literally. Because it's the best thing to have is when your application crashes, you get a stack trace. We basically TLDR. We use a library called bstacktrace. I've written this stuff before, but it's literally like bstacktrace header. Wait a minute. Okay, it is with the underscore. I didn't. Okay. Not. But yeah, the B user does this across basically all modern operating systems. It's like, 400 lines of code or whatever. You just drop that in your project. You wire up signal handlers, and you can just get that to print out when it segfaults, aborts, or whenever you just close it. Well, whenever you want, you can just get stack traces and print them out. So it's good. That being said, the way you get a line on a Unix operating system sucks, and it takes a long time if you use Vulkan. So if you're using it and you crash inside of Vulkan API call, beware, it could take 10 seconds because you have to use ADDR2 line to get the line number from a DLL for every single stack trace entry. And it takes seconds just to do one function, which is absolutely crazy. You know why it takes seconds? Because this guy here is like half a gigabyte, and it has to parse all that information. So yeah, that is that is a reality of stack traces on Unix operating systems. Unless you write your own ELF parser, I don't know. Yeah, definitely some chunky. Yeah, yeah, and you know why it's chunky? You know why it's chunky? Because Kronos love their CPP. You know what I mean? All the Kronos tooling. It's really great that the Vulkan API is a C API. But if you look at the rest of the tooling, it's just knee deep in C++. Like, it's just crazy. Like, you know, sure, you get the standard template library, so you can do arrays, yay. But the amount of string allocations that goes on within the Vulkan layer, like, I'm not sure how many people actually know. Like, I don't know fully, but from what I've witnessed, there's a bunch of little allocations that go on within inside the validation layer, and I can swear the reason why the validation layer is so slow, sure, is partly because they have to track so much state, but I reckon one of the biggest reasons is because they've just decided to use the standard library in C++ and just go all in on that. So that wouldn't surprise me, basically, is what I'm saying. Which is kind of annoying because it makes every application run slower when you use the validation layer. You know, you could just dump a core file load into the debugger, but I guess people these days strip their binaries and rely on things like. Yeah, well, that's the thing, Nico. You wouldn't be able to do the stack trace without the debug info anyway. Um, yeah, you would need that. But yeah, yeah, you need symbol names. But yeah, it's just nice when the program crashes to get that information dumped to a log file. That's the beauty of it. Whereas with a core dump is a little bit more technical than that. But those could also be sent back to the developer via some system or something, right? All right. So we're finding LODs. Um, so we need another data structure. This is so messy right now. Sort that out later. Right, so we've got these sort of push constants which go up from the CPU side. So we've got a buffer of volumes. We'll need to read write on those probably. We don't need the edits anymore. Read write cluster nodes. Free indices, we need those as well. What's your recommendation on handling device loss or device restarts? There's device restarts? I'm not sure what you mean by that exactly. But device lost, like a device loss happens because like the majority of the time because your shade has done something dodgy, right? Um, there's not really a good way of solving those. Um, so yeah, when you encounter that, the best thing, like the easiest thing to do, is just say the easiest thing to do is just crash the application. There's not much you can do when your shader has a bug and it indexes outside of an array and crashes the and crashes the system. If you're on NVIDIA hardware, and you have a dev build, a developer build, you can integrate Aftermath. And with NVIDIA Aftermath, you can basically get it to generate a crash dump file when you've integrated the SDK into your application. And then you can load up Aftermath and it can tell you what shader crashed at what instruction or what line of code. But on AMD, I think I'm not sure if there's one for AMD. I don't know that 100%, but I don't think there is one for AMD yet. And that is your best bet, is to basically do a whole bunch of testing and solve it. Otherwise, in release builds, you've just got to say a shader crash, and you don't know which one it is. So there's just no way to know. Or some shader took too long. Even when you don't have debug information in the other executable, you can split into separate file. That's how FreeBSD does it. If you want to debug something, you grab the core file, give it. Ah. Really? I didn't realize. Can you do that on non-FreeBSD systems? Can you do it on like a Manjaro? Can you have a separate elf file that contains debug info? Because that's how it works on Windows, right? And it's pretty handy when it works that way. For that reason, where you can just release. You can do that. Awesome. Because you can release the binary without the symbols. Like that's not going to matter for me. Because yeah, it's just not really going to matter. First of all, I'm using C, so I don't have absolutely crazy amounts of symbol names, right? And second of all, the code is kind of open source, so it doesn't really matter. But I didn't know that. It's very cool. That's how you can debug a kernel core dump after a panic. Ah. Right, so it's just in the where is the .debug file? Okay. No program header with debug info. Ah. Is the symbols file. Oh, right. Fair play. I did not know that. I did not know that. Interesting. So you'll need your free list indices. You'll need your volume spheres. Read write as well. Yeah. You're targeting a particular volume. So from that you can get the leaf nodes and start from the leaves. So we need a way to traverse up the leaf nodes. So the algorithm needs to be, we'll start off on the leaf nodes. Each thread gets a leaf node. You go up the tree, or you do your job, you do your work on that leaf node. You go up the tree, and you need to keep track of which threads have been here. And the thread that writes the last... How are we going to do this? You've got a children bit set. Yes. Yeah, I think this is where we can do it. Yes, there'll be a children bit set inside the cluster. So I don't think we need a lot of this stuff. Good. All right. So we'll basically, do the work of, so the first thing we're going to do is, well, we'll get the we'll fish out the volume. Just need this one. Yeah, so you fish out the volume. Then given the volume, you can get your leaf node, and that is dispatch index.x. This is just going to be a 1 by 1 by 32. Now we just want to say, okay, well, if the volume dot leaf nodes. Wait. Cluster leaf. Why is the IntelliSense always so bloody dumb? The problem is it's too smart, and it just can't follow code it doesn't fully understand semantically. So it's too smart. What are we looking for? Looking for the volume. Cluster tree leaf nodes count, that's right. So if the leaf node index is greater than or equal to this guy, then it simply just means we're going to return as we're out of bounds. Now, yeah, I think that should be fine. It's not using any wave intrinsics. May have good holidays in case I catch the next stream. Yeah, I think I probably will not be streaming until after Christmas, to be fair. But yeah, have a good Christmas there, Benny Montana, and I'll see you in a future one. Good to see you. But yeah, just as a bit of an update, I won't be streaming on Sunday's stream and on Tuesday's stream. So the Christmas Eve and and on Boxing Day, the streams are typically the days I'll typically be streaming. But seeing family and all that stuff. So I'll be resuming on the Thursday most probably, but I'll keep you guys updated in the Discord. More distraction. Okay. Then you can do the fancies like LLDB-C VM core.0 and then point to your place. Right, and the kernel. No, oh no, right. Okay, so you go into that, then you say you've created a core. Okay, this core dump thing or whatever. Add your dynamic symbols by that file, right? Then you do your backtrace, right? Yes, I'm sure you can probably get that to automate through some script or whatever. It's a bit fiddly, but I see that could probably get done as well. Nice. Awesome. Yeah, core dumps are pretty good. They should definitely get used in release builds, that's for sure. Oh, is it? Okay, that's good. So you just do this one. Nice. Yeah, I'm sure there's a way to get that to go right away. There's probably another flag you can do. That's sweet. Right, so basically we get the leaf the leaf node. Where's our boy? Where's our boy, Mr. Leaf? Volume cluster node equal this. So it's not really a leaf node index, it's kind of a leaf node. I guess it is. So you just want to work out this thing called like a node index. So you probably just want to stick it in a while loop. And you just want to say something like, well, my node index is equal to volume.cluster tree cluster tree take away leaf node index take away 1. And then you want to work out your absolute node index. So it'll just be ABS. Jobs are good. Yeah, I think we should try and maybe clamp this. We've got to figure that out later, but we're just doing a sketch of what this needs to look like. We'll get it compiled and we'll sort it out. So we got our node, and this is where we're going to do the work, right? We're going to, like, you know, simplify. Okay, so what's the thing we're doing again? So we go if what do you need to do exactly? So if the children so simplification and LOD. If children have a full set of spheres, right? If all children have a full set of spheres, then you know, okay, we kind of want to say for each maybe we do need multiple threads. Oh man. For each child, if all of their children have a full set of spheres, then, you know, create an LOD, a sort of higher LOD sphere. So that's one thing. The next one is for each child, if all their children have a full set of spheres, create a new sphere. Right. The next one that we want to do is if all of the children, if which one is it exactly? Yeah, so if they have a full set of spheres, if they have a full set of spheres, oh, which one is it exactly? Yeah, if they're a full set of spheres, then create a sort of higher LOD sphere. But then we want to say if they and if they and if all of the children are surrounded by other clusters, right? Is it full clusters? Other full clusters, or yeah, because if you have a 2 by 2 by 2 and it's got to be surrounded by another set of full clusters. Yeah, they're all surrounded by other full clusters. Then delete the children, and we'll just have that high level of detail sphere. Okay, so that's the basic idea for that one. That's how we end up saving a whole ton of memory, because that will actually happen, a whole load, when you just paint a load of spheres down. It's going to happen. So that being said, you have 8 children. So if you're doing one thread processing a node, that doesn't seem like the best thing, right? So it's as if we want probably maybe an 8 by 4, because that's 32, isn't it? So each x is gonna be a sphere or a child. Oh, which one? Yeah, that way we can process 8 children at one time. And then we can also search. See, this has got to do a search operation though. Yeah, and then you do your searching across 8 at a time and report back. There'll obviously be some places where we'll have to synchronize, but it should be alright. So the y should be the leaf node index, and the x, but the local index, should be the child index, right? Oh, I should do it the other way around. Let's do .x.y, and we'll do a 4 by 8. And we'll do this sort of sphere. Sorry, children. Alright. I think that seems pretty alright. So you go over... Okay. So now we've got to deal with the traversal. Like, how do we... Like, so after you've done all of that, right, we now need to traverse up the tree. And we need to say, hey, I've been here, and then terminate the thread, unless we're the last one to be here. So we need... So we can tell that, if we look at the cluster node, we've got a children bit set. So you know how many children are going to come up and say, hey, I'm here. But you need to have another bit set, which you can atomically set, and is shared between that's shared between all the threads running on different compute units, where you can basically set the bit set, and then get back a bit set, you know. And if it's equal to the children bit set within that parent node, then we're the final thread to get here. And then we don't terminate, and then we carry on up the tree, repeating the work. So where is this other bit set going to go, which we're going to build, which is going to initially be set to 0? Where is this thing going to be? It's probably got to be in a buffer, and it's also got to stay persistent. And if you were, and another thing that's kind of crazy about it as well is I think it might have to be persistent because you might have to call this thing multiple times on the same tree. But maybe there's a way to tell whether or not these nodes are complete. We could put a little flag in there and be like, oh, this thing is complete. We can just say like, is complete. And it could be a nice little thing where we just say, if node.is complete, then we just terminate here. And we just launch across all of the... It'd be a bit of a waste, but I'm not sure there's a way we could solve that problem. Because the issue is we're going to have a volume, 1024 cubed volume, and we can't quite do that all in one go. So we have to do like a small piece of it. Maybe 256 squared. But maybe 512 squared. Maybe that's fine. Because we have to pre-allocate memory for the worst case. So after we've done one area of it, we have to call this refine, which allows us to heavily simplify and remove a lot of this, basically free up a lot of memory, so we can go again. So some of the nodes are going to actually be complete. But maybe there's a way, there's a leaf node. So the leaf nodes will retain the order, right? So you're just going to add them past a certain point. Meaning we could probably just go, oh yeah, by the way, yeah. So the is complete is actually not a good idea. It's interesting, but not a good idea. There's a better way. And that way is simply just, we can have it passed in and say, right, so to get the children, you just go, okay, take volume dot cluster tree leaf nodes count plus leaf node index. And if you did it that way, where it goes to the beginning of where the leaf nodes are, yeah, so it goes to the beginning of where the leaf nodes are. Whenever we make any more future leaf nodes after we've done the first refine, they are always going to come they're always going to be prepended to the beginning. Yeah, they're going to be prepended to the beginning of that allocation. So it means then when you offset this, we're only going as far as it's being told by by this number here. Excellent. To do this many leaf nodes. Then as you go up the tree, if you come across the same leaf nodes which you've already kind of processed before, but they wouldn't have been finished, you got to somehow retain the bit set for them though. That's the problem. So we can actually use the high bits within this bit set. It's a little crazy. But we're only going to need 8. Okay, this can work. We're only going to need 8 bits. Okay, so it is kind of ensuring that we do keep this, but it's fine. So the first 8 bits are for the children. The first set of 8 bits, the second set of 8 bits are for refine LOD, are for refine LOD, are to say are for the children that have visited in refine LOD, and then that makes it persistent. And then that makes it yeah, it's actually probably a good idea. Yeah, that's really good. So I think we'll write that code out first, traversing up the tree, and then we can literally just like do this one. Awesome. Right, I just need to quickly go and get another drink, and I'm just going to check on the family, and then we'll write out that sort of traversal code as we go up the tree and terminate threads, and then we'll get going on this guy. Right, BRB. Alright, welcome back everybody. So I'm going to start some H2O. So. Trying to balance my phone somewhere. There we go. Right, so. Oh, I could stick over here actually. I've got a look. Oh, that'll work. When it doesn't slide. What are you doing? There we go. Okay, so we want to do this traversal code, and we found out that we can store it in the bit set of the node. So basically we need to know. So right, is the child index going to get updated? Excuse me. So the child index, is that going to get updated at some point? Because that's not going to be the same every time. So we need to make sure when we go up the tree to the one of the characters is parent, the child index gets updated. So I'm just going to do that. So we shall remember. So if child index is equal 0, no. Okay, so we need to know the bit that we're going to set. The bit that we're going to set. Hey there, Tar. What's up? In this town we call Eden. What does that mean? What do you mean? Where's this coming from? So we're essentially just gonna, yeah. So we need to say, given. Now I have to get this. Right, children bit set. Now we're gonna say, and. Okay, no. We do the atomic or E32. Take the address of that. And I'm going to roll a lovely bit on there. So this is the bit to say that we've been here. So this is the visit bit. So it's one shift left. Whatever the child index is, plus cluster children count. Now the reason why it's plus children count is because the first 8 bits is for the children, and the second 8 bits is to use to say we've visited them in this shader. It's just some place where we can store the data, and turns out we've got 3 bits to do that. So we just want to say the visit bits from the children bits. So when you do your visit bit, you'll get your bits back. You get the old bit, yeah, you get the bits back. The old bits back. So you put in your visit bit, and then you do OR visit bit because you get the old visit bits, and you need to OR the bit you've set on it, right? So now you got your bits back. And now we've got to figure out, based on the bits, were we the thread which completed all of the children visiting this node, right? Are we the last child to visit the parent, basically? Oh wait, we haven't got the parent. This should be the parent one. whoopsie. Parent ABS parent node index node.parent node index, and I've got to do some silly thing like this probably, I don't know. Alright, we'll sort that later. So given this, rightio, so you visit bit. Now, given the bits you get back, you just need to do this, right? And it looks pretty cool. If bits shift right equal, this is not going to be readable, but hopefully the comments will make it make sense. Equal bits and so we'll call it like children. I don't know, whatever. So this is saying basically we are the last this is a good test for my compiler, I think. We are the last child to visit the parent node. So we must carry on. So yeah, we must carry on. Carry on. I don't know, the torch. I don't know. There we go. So this means we need to update a couple of things. The node index needs to get updated to the parent node index. The child index, then we need to figure out what child are we? I think I maybe got this wrong. So I start on the leaf node. I sort out all of these guys. I need to work out what child index I am here. So what is my child index now? So you know that based on the node. Mod to it, probably. Yeah, it's the mod to unravel thing, isn't it? Where when we flatten it. this guy. So you got to flatten node dot depth dot near node dot bottom node dot left, and that'll get your child index. As you go up the tree. That's alright. Yeah, I think that makes sense. We'll have to double check this, but I think that's the traversal code going back up. Cool. So then now we've got to actually do the actual work, and that is for each child, if all their children have a full set of spheres, then create a higher level of detail sphere. But then also, if all of their children, yeah, for each child, yeah. But then if all of their children are surrounded by full clusters, then delete the children. So, okay, so for each child, while you're doing it, you know, the beauty is one thread is a child node. So it's pretty easy. So you've got to get your child node. So the child node, what about the child node? No, you have to fetch it out. Anyway, so what we got to do? Yeah, you've got to visit the child node yourself. Yeah, so ABS. So given node dot children node indices child index, get yourself one of these guys. Then you basically just need to look at the, there's what do we need to look at? There's spheres start index, but what about it? We need to know, we should really kind of know how many of those spheres are actually, you know, we could go over all of them, like, you know, one at a time, and check if the radius is not 0. But that's not going to be fast, is it? So it'll probably be better if we split this into a 24, 8. We don't even need that. You need 3 bits. And then you need basically 32. 3 take 32. Or 30, yeah, take 3 from 32. 29 bits. Let's do spheres count. So when we set that up, which is just up here, we've got to make sure we actually set up the spheres count as well, yeah, because we have that already. All right, so now when we're in this sort of refining code, we can literally just go, oh, so those spheres you've got there in the child node, is that equal to 8? Now you have to do that for all of the child node. Yeah, for all of the children. Um, hmm. So the problem is not all of them. So you kind of want to only say, right? Put this up here. You want to go, oh, by the way, if there's a full set of children, is that right? So yeah, that's something we forgot to kind of write in this comment. We need to have a full set of children. No, that's not right. Right, for each child, if their children have a full set of spheres. Right. Alright, okay. Uh, so we might need to do a for loop now, actually. We can do one of those iterators based on the bit set. Still, while we've got these children bits to look at. Yes, you'll basically just get the bits. So you'll get like the children bits. Or bit set. While children bit set. See, maybe this child index shouldn't be used like this. I'm trying to think what was best to do. Because you've got a node. And it has... No, it's too many layers. I'm thinking about this completely wrong. For each child, if all their children have a full set of spheres. No, that's written completely wrong. Yeah, I'm reading that wrong, Yeah, so for each child, if all their spheres have... Yeah. Okay, so we don't need that. We just need to say, hey, if one shift left child index... So if that child exists for this thread, we're then going to access that child like so, get the spheres count. If that is a full set of spheres, then we want to create a higher LOD sphere for that. So that's equal to cluster spheres count. This is where we create the higher LOD. Okay. Easy peasy. So the next thing then is now given if that child is it that child cluster? So if that child cluster is surrounded by if that child cluster is completely surrounded by oh, I didn't realize you could do it at that level. So we could do it where is if a single cluster is completely surrounded by other clusters from all, how many directions would that be? Including diagonals? So it's 6 plus 8 more, isn't it? It's a lot of directions to check. But so if they're completely surrounded by clusters or high level detail version of those clusters, whatever, then you can delete that child. Right, so we need to have a way of working out somehow. We have a tree, so we can traverse the tree. But but the problem is that tree is going to be mutated in parallel. So traversing the tree is probably going to be a bit silly, since we're going to have the ability to destroy parts of the tree. So we basically need a way of saying if it's completely surrounded, right? So if Boolean, if the cluster, or if the child is surrounded by other clusters, right? We'll figure that one out in a sec. But if it is, then we need to, basically delete that child, right? And then we also need to figure out, hey, if all of the children got deleted, then is this thing a leaf node, right? So now I need to check if this node is a leaf node, move it. Move it from the non-leaf array to the leaf array, right? So that's a more refined version of that comment we just deleted. So I'm not fussed about this code. It's dead easy. I'm more fussed about this code now. This code could have problems, but it's not as big as a deal as this one. So let's got to figure out how we're going to do that one now. Okay, so how do we know of a cluster? So, given a cluster in 3D space, right, it's just a 2 by 2 by 2 set of spheres. Those 2 by 2 by 2 set of spheres. Oh yeah. So they make up a cluster, and they're on a grid. If they are completely surrounded by a set of other clusters, then they're probably not. Yeah, so they're not directly visible. So we can just replace that with a larger. We can just delete that child cluster basically, and then the parent has a leaf sphere rather than a high LOD sphere, right? It's just it is the lowest sphere. There's no high level of detail. Man, did I say higher? I meant lower. Low LOD sphere, damn it. Okay, so how are we going to figure that out? Because we can't go and traverse the tree because it's being heavily mutated just by the fact of this happening and this happening as well by moving it. So the moving might have to be deferred. And so I guess maybe there's a way to say we don't mutate anything yet and we defer it to a second shader that just runs after it. So you just mark this child for being deleted, put it in an array somewhere, and then we'll just go and delete everything. That's one way of solving it. It's not too difficult to do that way. This one will be like, well, so you can run over and do all the deletes. And then this one can be like, well, I want to move some nodes from being a non-leaf node to a leaf node. So that one, you basically create a hole in the array, and it needs to be patched from the back. So you've probably got to do that in a single-threaded manner. No, you could probably do it in a multi-threaded way. Probably would do it in a multi-threaded way. But yeah, if you did these later, that would then mean you could technically traverse around the tree here and search. You don't have to traverse all of the nodes because technically you're in a cluster, right? And only when it's full. It's in the wrong place. So technically you're in a cluster, so that means, or this cluster here tells you instantly 3 of the neighbors because your child well well, sorry, it'd be 7 of the neighbors, wouldn't it? Yes, this instantly tells you about 7 of the neighbors. So you only really have to look. So if I can draw this out, might be easier. So you have a parent node which has 8 children, but for the sake of simplicity, let's do 4 children because I can draw it easier. And it's the 2D representation anyway. And then there's a sibling node. With its 4 children. And then there's a parent node up here which links these boys. Right. So if we've got a thread which is working on one of these children here, right? Imagine these are all completely filled with spheres. These guys, all of them are. So the fact so if this one's filled with spheres and you've made the lower level detail of that group of spheres in this node, or you made the low level detail sphere in that node, you then get a chance to go, hey, am I surrounded? Or you know instantly about 7 of its surroundings, right? You know, so given it in 2D, right? You've got one on the left, one on the right, one above, one top right, one top left. So you've got 9, right? Or you got 8 siblings in 2D. But in 3D, it's like 8 plus 6, I think, is something like that. Anyway, I forget the number. That's the idea. This is the current one we're checking. This guy here, this cluster here. So we just need to know, hey, they all... So regarding the current setup of these clusters, right, they're 4 in this case in 2D, but obviously it's 8 in 3D. It could be... It could be these 4, right? It could be these 4. It could be these 4. Or it could be these 4. That you just instantly know. Is that right? Do you instantly know them? Or they're your siblings? So you're going over all of the children at once. You're going over all of the children at once. So you could theoretically build... yeah, so not all of them will come into here, right? Because of this branch here. That only comes here if they have a child. So I guess you can just say, hey, yeah, so you want to basically say if the bit set is completely filled with children, so it's completely full one, and so this is completely filled with children, and Yeah. So you say if it's completely filled with children and all of those children have spheres, so you kind of have this Boolean sort of like sent across the other threads, I guess. And all of them have a full set of spheres. Yeah, well, we have to make sure it's not, it has to be a leaf. And they have to be leaves. How do we know this one is a leaf? Yeah. So if is leaf. If child node is a leaf, you can also just check. Whether we're deferring it, you won't quite know based on the index itself. Right, so given the bit set, if the child node is a leaf, you still solve that problem. Okay, so you would instantly know somehow, like you can instantly kind of know about one section of them, but you're still missing these ones, right? So you kind of have to search for these guys, which kind of increases by 3 times. Is that right? Yeah, it kind of increases by 3 times on 3D. Right, because you've got the ones coming toward. Oh no, by 2 times. So you got individually go and search for those or something like that. Is that right? So I'm trying to think, is there a way? Hey there, Mr. Toggle. How's it going? Thank you for the raid, sir. How you been? How's it been? It's been a while. It has, isn't it? Merry Christmas to you, sir. Merry Christmas. How you been gaming? Awesome. Wait, what game you been playing? Yeah, I've been doing a bit of gaming as well. I've been off all day. I've been playing some games. Crazy, right? So you game Engine Vulkan Linux or for now? Awesome. Thank you for following, sir. Appreciate it. Welcome, welcome, welcome. Outer Worlds, right? I've not actually played that one. I played the Outer Worlds, you know, but yeah, not the Worlds. Yeah, fair play. Yeah, that's cool. Awesome. Yeah, just we're just currently building a game event engine. We're knee deep in kind of executing the plan of doing level of detail of tons of spheres and you know building a 3D volume filled with spheres, all written in C using nothing but compute shaders and stuff like this. So we're just kind of trying to get something very minimal working. I don't know if I can go and show VOD. Those have popped in. VOD. Oh my days. Ugh. Here's past me. Look at me go. There's some somewhere here, wouldn't it? Probably a lot less aggravating. Fair play. Mm-hmm. But yeah, how's the projects going, Toggle? And how's the family? How's family going? Where where where's my spheres? I just want to see spheres. Here we go. Enough complaining and you get there. So yeah, we've basically got multiple instances working. I don't know why I'm not seeing it here, but we've got got free cam, and we're just basically doing this is the old version, where it's got 3D volume of spheres, but it's not many spheres. But we're trying to push spheres to hopefully go down as small as 1 millimeter, and it's going to be pretty crazy. But we'll see how that ends up going. But we've written out a plan. It seems feasible. We're gonna have multiple instances, different volumes. You can put a bunch of volumes together and make an overall thing, basically. But yeah, very early days still. We're just trying to see how many spheres we can push on the screen first, and then we'll do other shader thingies to make the spheres not just normals. No, they're just spheres. No sinus and fields. No, not doing sinus and fields. I want to do something a little bit more unique, basically. So we're just ray tracing against these spheres. I've got 3 different ray tracers, because I don't know which one is going to be better. I've got different strategies on rendering them. So we've got 3 different renderers. We've got a screen space binning. We got frustum space binning, so frustum space voxels, and then we've also got a BVH that we've handmade as well. So yeah, got all that I've been playing about with. Yeah, just doing some ray tracing. It's all compute-based ray tracing. It's not any of the fancy API. Almost done. I have 1 big bug left and 1 feature. Awesome. Good stuff. It's happening. It's a good time. Family's good. How's my life going? Yeah, it's good. We're just been chilling, hanging around with the baby, looking after the baby. Super cute, and also a lot of work as well. So many little qualities where you're like, oh, it's so cute, and it's a lot of fun. Need to go have sleep, but nice. Ranger, thank you. Thanks, I appreciate it, sir. Have a good one. Good night. Yeah, I've got my own maths library, basically. I've got one that I've put in my custom C compiler. So I've got a custom C compiler called HCC. It compiles the sphere V, so you can use C as a shading language. It does vertex shaders, fragment shaders, and compute shaders. We're obviously only using it for compute shaders for this project. It comes with a maths library which does a bunch of useful things, but I've gone and actually implemented some matrices myself, for a more compact matrix, basically. So I'll drop that in the chat, just in case anyone wants to take a gander. But yeah, yeah, so that's pretty cool. So as you can see, we're running C here, basically, and it's all we can share structures, functions. It's all, yeah, we can even like print from shaders as well, which is not something you typically get to do. So it's proper powerful stuff, and yeah, I'm not sure why in 2023, nearly 2024, we don't just have one language that we write in. It's really silly. We have to have a shading language. The whole concept of a shading language is basically done, right? It just shouldn't exist. I think there's a few people who disagree with me on that one, but they probably haven't had a taste of if it was just one language, right? Like when you have just one language, things are very simple. when it comes to interop. So yeah, we're just trying to figure out how we're going to do this. How we're going to figure out if a cluster, and a cluster, by the way, is a 2 by 2 by 2 of spheres. How if it's completely surrounded by another cluster? I don't know how I'm going to do that. There must be a very... I don't want to visit every node, because that's... So in 3D, so that's 3 by 3 by 3. Is that right? Which is 27, take 1. It's 26 nodes to check. Bear in mind, 8 of those come for free. There's still a lot of nodes to manually check, right? So I don't think that's viable. But something we could do is go, hey, by the way, if yeah, so given wherever this thing is, right, this your cluster is that you're checking is surrounded, you could we could do something a little bit less optimized for space, but it's probably just fine because it'll be optimized for speed instead. So the benefit is for this one is you simply just check the sibling. Right, so we've got this. Let's get this right. So this white cross here is this white cross here. Right, and then we'll do the pink cross. And then this pink cross. So I think the beautiful thing we can do is, rather than checking all of the, the children, which would just be ridiculous, instead, so we're processing this guy. You just want to somehow keep in these nodes, like, hey, of all of the children, have all of my children got a full set of spheres? Wait, is that what we're looking out for? Yeah, if all of my children got a full set of spheres. If they do, I can mark something in me. And then all you have to search for is your siblings, right? But there's 8 of your siblings, so you could just put it in the parent of you, right? But then that doesn't make sense because that's the parent of you there, which means that one there. But if your cross was actually here, right? That's not in the middle. You're technically like dangling over two cluster trees, right? You're half in one and half in the other. So the middle. I love C for simplicity, I love Rust too, but things like recursive data structures using graphs is mess in Rust. Yeah, I can imagine with the borrow checker and stuff like that, isn't it? You basically have to use indices, right? Like, when the borrow checker gets in the way, you just use indices. And that is your reference, right? Which most of the time in C, you typically do that anyway. And when it comes to shader code, you have to do that because you don't have pointers, right? Yeah, so in this case, we'll be going over to, like, to know if you're surrounded, you've actually got to visit that cluster, that cluster, that cluster, and that cluster. So you still have to search for some clusters, you see, like 8 different clusters, and you have to search for those through those manually. Um, uh, See, I think there's a way where we can simplify this and it'll be elegant, right? I have a feeling there's a way where this can be simplified, but I think my brain has been doing too much today, and it's just not quite there. But we've got to get it all mapped out now, and we're pretty close um, to like having these things fully thought out, and then we've just got to wire the whole thing in and double check it all, obviously, because we want to be running this thing and not crash and burn my PC. So yeah, I've just got to have a think on how I want to achieve this. There's probably an elegant way. Right, I got a jam because sleep. But yeah, thank you for coming, everyone. I'm not on Sunday, and I'm not on Tuesday. Family stuff going on. Christmas, that's Boxing Day, and sorry, Christmas Eve and Boxing Day. Seeing family. Possibly I'll be back on the 28th. If not, it will be the following Sunday. But I'll keep you guys posted on the Discord channel. So there's a Discord over here. Oh, oh my days. Hey, Coffee Lover. Thank you so much for raid, sir. Very much appreciate it. But I was just about to jam myself. Thank you so much for the raid. Appreciate it, sir. And also, Merry Christmas. Welcome, raiders. Yeah, I've just got to jam myself. But I was just about to say there's Discord where I'm going to post some updates on what sort of my schedule is going to be over the next few days. So give a last miles raid. Right. Have a good Christmas, everyone. And I'll see you after. Yes. I'm sorry. Apologies. But yeah. Thank you for the raid, sir. Appreciate it. But yeah, and also have a good Christmas, everyone. And have a good night as well. Radio. Catch you later, guys. Bye bye.